Welcome to this video. In this video, I'm going to test various assumptions of classical linear regression model. In order to do that, I would request you to watch this video up to the end so that you could understand the whole process. Let me remind you that the simple linear regression model is specified as follows, and the key assumptions associated with the simple linear regression include: the errors are normally distributed, they have constant variance, and they are independent of each other. There is a linear relationship between the expected response and the explanatory variables. In contrast to simple linear regression model, the multiple linear regression model is specified like this. The key assumptions are that the errors are normally distributed, they have constant variance, and they are independent of each other. There is a specific relationship between the outcome, the expected outcome, and the explanatory variables. My dear students, I want to share some notes regarding diagnostic tests of the regression model with you. And let me remind you, these assumptions include linearity of the data, normality of the residuals, homoscedasticity of the variance of the residuals, no autocorrelation or no serial correlation. We should check whether or not these assumptions hold true. Some potential problems that may appear are non-linearity of the outcome predictor relationships, heteroscedasticity, that is non-constant variance of error terms, presence of influential values in the data that can be either due to outliers or due to high leverage points. All these assumptions and potential problems can be checked by producing some diagnostic plots to visualize the residual errors. These are the various scatter plots that can be checked for visualizing various residuals, and they are basically 4 diagnostic plots. The first diagnostic plot is or the scatter plot is that of residuals versus fitted outcome variable, and this basically help assess linearity and homoscedasticity. Ideally, the residuals should be randomly scattered around 0 with no discernible patterns. The second scatter plot is normal QQ plot. This plot checks the normality of the residuals. If the residuals are normally distributed, they should fall on the along the diagonal line. The third scatter plot is scale location, and with this we can check homoscedasticity of the residuals. And the fourth scatter plot is that of residuals versus leverage, that deals with the outliers and leverage of data points. I would recommend you to read these notes so that in your own data, in your own regression model, you can express the various scatter plots of your regression model. So I assume that you have read these notes. So let me go to R. Here is how R Studio looks like. Let me open R script, and here I am now in the text editor window. First of all, I would like to import my data set that I'll use for diagnostic tests of the regression models, and my file is on desktop. The name of the file is hsb2, which is here, and well, this shows that my Excel file has been imported into R environment. The name is hsb2. It has 200 observations of 11 variables. These are the 11 variables. Let me first of all use this command. That is for regression. After this, I'll specify a multiple linear regression model by writing MLR, multiple linear regression, and this is the argument LM, my dependent variable, followed by a list of independent variables, and data set equals HSB2. If I run, it has estimated this model, but I want to see summary results of these models. So summary MLR, and this will give me the summary results. So since I have already explained and interpreted this model in my previous video, that is video number 552, but once again let me briefly explain it. These are the residuals, minimum value first quarter, this is a median, this is third quartile, and this is maximum value. Here are the coefficients of the model. So we can see estimated coefficients of the intercept. These are the estimated coefficients of the three variables: math, reading, and writing score. These are standard errors, these are t values, and these are associative p values, and it shows that all the three explanative variables are highly statistically significant, and they have positive effect on the dependent variables. This is the root mean square error, or the residual standard error. This is equal to 7.055. This is the r squared, unadjusted r square is equal to 0.50, adjusted r square is equal to 0.49, and this is the f state value, and its p value is this. So this shows that the overall model is significant. After this, I'll visualize the scatter plots of this model. So plot MLR, and if I click on this, now it says hit return to see the next plot. So here is the first scatter plot, that is residuals versus fitted. So we want to visualize residuals against the fitted values of the dependent variable, or the fitted value of the outcome variable. Ideally, there seems no problem of linearity and heteroscedasticity in this model, because the residuals are randomly scattered around this zero line. This is a good sign. The second scatter plot is that of QQ plot, and this shows basically whether the residuals follow normality or not. Residuals are normally distributed if they approximately fall on the diagonal line. So we can visualize that these residuals fall on the approximately on the diagonal line. So this is a good sign, and we may visualize, or we may conclude that residuals are normally distributed. The third scatter plot is that of scale location, and with this file we can visually check whether there is a issue of heteroscedasticity or not. Now if you look at these residuals around this red line, that they are randomly scattered without any discernible pattern. There is no specific pattern of these residuals against this red line, so it doesn't pose any problem of heteroscedasticity. Finally, we have another scatter plot, and that is the scatter plot of residuals versus leverage, and this deals with the outliers and leverage points in the data set. So now I will formally use various different tests. That is, we will check whether the independent variables are multicollinear. When there is multicollinearity problem, we will also check normality of the residual by Shapiro-Wil test. We will also check autocorrelation with the help of Durbin-Watson test and Breusch-Pagan test, and that is not Breusch-Pagan, Breusch-Godfrey test, and finally we will test issue of heteroscedasticity using Breusch-Pagan test. So first of all, I would like to check multicollinearity, and we can check multicollinearity with the help of VIF, that is variance inflation factor. So before that, let me check this library. Sorry, it should be here. Library car, and I should run it. After this, I'd specify VIF values followed by this argument VIF and MLR Yes, the VIF values have been created. Let me print these values. VIF values. So, okay, these are the VIF values for the three independent variables format. The VIF value is 2.06. For read, this is 1.98, and for write, this is 1.1798, almost 1.80. Experts and researchers have reported that VIF score of 5 and above indicates high multicollinearity. Since in this case these three values are well below 5, so it indicates that there is no problem of multicollinearity in this model. After this, I'll check normality of the residuals, and normality of the residuals can be checked with Shapiro test, and Shapiro test can be run like this. This is the formula. How can we check Shapiro test? So here is the Shapiro-Wil test value, WO test value, and that is 0.995 with its associated p value of 0.57. So here in the multiple linear regression model, the null hypothesis is that the residuals follow normal distribution. Since this p value, this observed p value of 0.7517 is greater than 0.05, so we reject the null hypothesis and we conclude that the residuals follow normal distribution. They follow normality. So this is a good sign. After this, we will check autocorrelation, and autocorrelation or serial correlation can be checked either by Durbin-Watson test, or we can also use Breusch-Pagan test. So first let me use Durbin-Watson test, and for Durbin-Watson test I'll create Durbin-Watson test, and the argument is DW test for this model MLR. Clicking on run, let me see where is the problem with this DW test. Sorry, it has some problems. So how can I do that? This is in the LM test, so I think I should first use the library LM test, and if I do that, okay, so now let me check DW test. this. Okay, now it has been created. So DW test has been created after using the LM test, because this test is in the LM test package. After this, I'll print result of the DW test. DW test. So here are my results. This value of 1.91 is for the Durbin-Watson test, and its associated p-value is 0.26. So the null hypothesis is no autocorrelation. The alternative hypothesis is that true autocorrelation is greater than 0. Since the observed p-value is greater than 0.05, so we fail to reject the null hypothesis of no autocorrelation. So this is a good sign. It means that in this model there is no problem of serial autocorrelation. This is good. After this, we will test for heteroscedasticity, and but before that, let me also run another test for checking autocorrelation, and that is Breusch-Pagan test. And this Breusch-Pagan test can be checked by this command. And this is the LM test value for Breusch-Pagan. Its value is 0.3131, degrees of freedom is 1, and p-value is 0.5758. The null hypothesis of no serial correlation or no autocorrelation cannot be rejected, so we fail to reject the null hypothesis of no autocorrelation. So there is no issue of serial correlation or autocorrelation in this model, both by Durbin-Watson test and by using Breusch-Pagan test. After this, I'll check heteroscedasticity issue by using Breusch-Pagan test, and the formula for the Breusch-Pagan test is BP test, and within parentheses MLR. And if I run this test, here are the results of the Breusch-Pagan test. The Breusch-Pagan test score is 2.5459 with degrees of freedom 3. The associated p-value is 0.467. Here the null hypothesis is that the residual variance is constant, that is, they are homoscedastic, and the alternative hypothesis is that residuals are heteroscedastic. Since the observed p-value of Breusch-Pagan test is 0.467, which is greater than 0.7, which is greater than 0.05, so we fail to reject the null hypothesis of homoscedasticity, and we conclude that the errors or the residuals are homoscedastic. There is no issue of heteroscedasticity regarding the variance of the error terms. So these results shows that there is no issue of multicollinearity. There is no issue of the residuals are normally distributed. The residuals are independent of each other. There is no issue of autocorrelation or serial correlation, and the variance of the residuals are the constant. So there is no problem of heteroscedasticity, there is no issue of autocorrelation, there is no issue of multicollinearity, and the residuals follow normal distribution. So these are very good signs for this model. So we can report the results of this model. Since this is hypothetical data, you may also try to have a model like this which has no multicollinearity issue, where the residuals follow normality, and autocorrelation and heteroscedasticity are no problem in your model. So I hope this is quite helpful for you, my dear students, colleagues, and friends. Kindly subscribe to the channel and don't forget to click on the bell icon so that you can get timely notifications about my other videos.